Hello class, these are our notes for section 711 in Algebra 1. What are perfect squares? So a perfect square is an expression that is something times itself. So for example, we can say that 49 is a perfect square because 7 squared is equal to 49. Or we could say 16x to the fourth is a perfect square because we could write it as 4x squared quantity squared. Expressions that are perfect squares are written in factored form, and then in standard form, there is a pattern. And we're going to just do a really quick investigation of this pattern. We want to take ax plus n, and then we want to square it. So let's write ax plus n times ax plus n. So first, we multiply ax times ax. That's going to be the quantity ax squared. Then we're going to multiply ax times n. So I'm going to write ax together times n. Then we're going to multiply n times ax. That's going to be another ax times n. I can write the multiplication in whatever order I want. My last term is going to be n times n. That's going to be n squared. So my first term is that ax squared. My middle term, I have 2 of the ax's times n's. And my last term is n squared. So I really like to think of this as like ax is the first thing in my parentheses, the first term in my binomial, and I have that ax squared. So I like to think of it as taking my first term and then squaring it. If I look at the n squared, it's really like taking my last term. If I look in the binomial, my last term in each of those binomials is n, so I'm taking my last term and squaring it. And if I look at the middle part, it's 2 times the first times the last, because I had to double it. So 2 times my ax times my n is 2 times the first times the last. And obviously we could write this a little bit differently, right? I could write it as a squared x squared. But I find for the purpose of just trying to write this pattern out quickly and use the pattern, it's easier to think of it as just the first term squared for me. All right, we're going to go ahead and practice using this pattern a little bit. So let's look at the following binomials. We want to be able to multiply them out, and we want to be able to use our pattern. So my first term is the x. I want to take that and square it. So I have x squared. My middle term, I want to go ahead and multiply my first and my second term. So x times 1 is a 1x, but then I want to double it. So 1x doubled is 2x. Plus, then I want to take my last term, which is a 1, and I want to square it. And 1 squared is 1. Let's go ahead and try it on the next one. So my first term is the 2x. So I want to take that entire 2x, and I want to square it. That's going to be a 4x squared. My middle term, I'm going to get by multiplying the 2x and the 5 together, right? I want to do this one times this one, 2x times 5, and then I want to double it. Oh, you know what? These are wrong signs here. We need to fix this. They're supposed to both be minus signs. Otherwise, they would be, this is not what I'm looking for, huh? So let's make them both minus signs. So that means I'm not going to have a plus here. I'm going to have a minus. So we're going to have minus, and then we want to do the 2x times 5, and then I want to double it. So I'm going to have 2 times 2x times 5. And then my last term is going to be a plus, because it's negative 5 times negative 5. That's going to be a 5 squared. So the first one I kind of multiplied out in my head. The second one I'm definitely doing a lot slower, because there's a lot more parts. So my middle term here would be 2 times 2 times 5, so 4 times 5 is going to be a 20x, and the last term would be a 25. So I just wanted you to see how we would use that pattern. You're going to go ahead and try C on your own. Go ahead and just pause it, but I am going to explain it, so you'd have to pause. So first term is x, so I'm going to have an x squared. My middle term would be x times 4, so 4x, but doubled, and there's a minus sign, so minus 8x. My last term is the 4 squared, so 16. Okay, on the next three, we're doing the reverse. We know it is a perfect square, and we're going to factor instead. So to factor it, if I know it's a perfect square, I'm just really looking at my first term and my last term. And there's another mistake on this. This one should be an x squared. I thought I fixed them all, but I did not. All right, so if it's x squared plus 6x plus 9, when I go to factor it, The square root of x squared is just an x, and square root of 9 is a 3, so I should have an x plus 3 times another x plus 3. We could still look to see if our middle term works. And I know 3 times 3 is 9, 3 plus 3 is 6, so it absolutely works. We could use our old style of factoring for this as well. This is going to be the quantity x plus 3 squared. On the next one, I can see that 4x squared is really the quantity 2x squared. 9 is 3 squared. And is my middle term doubled here? So 2x times 3 is 6. Doubled is 12. So this one doesn't actually fit that pattern. So I don't know if we meant to have a mistake here, so it's not factorable, or if we meant to make this a 12 instead. So I'm just going to write as is, not factorable. And it could be by the time that you get this paper, it's been fixed. And let's rewrite it as 4x squared plus 12x plus 9. So again, because 2x times 3 is 6, but my middle term's doubled, it should be a 12x. And this one would factor to 2x plus 3 times another 2x plus 3, which is the quantity 2x plus 3 squared. All right, on the last one, let's see what we got here. So 9x squared would be the quantity 3x squared. And then over here, we just have a y squared. And then let's check our middle term. 3x times y is a 3xy, doubled is 6xy. So this one's perfect. So 3x in both of them, minus signs in both of them, minus y, and I could write that as the quantity 3x minus y squared. We really want you to write it as a squared quantity, if that's possible. All right, so now we're going to solve equations by factoring. So I could subtract 25 on both sides, and then I could refactor. But the idea here is that we look at this and we say, hey, this is a perfect square. I can factor it right away. This is the quantity x minus 9 squared. And that's because 9 times 9 is 81. Negative 9 times negative 9 is 81. When I add the two negative 9s together, when I double it, I get 18. So right away I can see that this is a perfect square, and it's equal to 25. So if I have a perfect square equal to another perfect square, I could just go ahead and take a square root on both sides. A square root of a square is going to give us an absolute value, and the square root of 25 is just a 5. So remember, to get rid of those absolute value signs, it's like we trade each of them in for a negative or a positive solution, because I could take the absolute value of a 5 and have it equal to a 5. I could take the absolute value of a negative 5 and have it equal to 5. So my x minus 9, the stuff inside my absolute values, could be equal to a 5 or a negative 5. So I'm going to go ahead and write those two equations. And I don't care which order you write them in. It's probably nicer to have the negative one first, but not always. And I really don't care for my students as long as you remember them both. So let's go ahead and solve. We'll have to add 9 on both sides. So x is either equal to 14, or when I add 9 for the second one, I have x equal to 4. So 14 or 4. We're going to do the same thing on this last one because I recognize right away that 121 is an 11 squared, and 9x squared would be the quantity 3x squared. So let's just check our middle term. Does our middle term work? 3x times 11 is 33x, doubled is 66. So we have already factored this. And I happen to know that 225 is 15 squared as well. So we totally have perfect squares here. So we're going to write this as 3x minus 11 squared. And then I might even write 15 squared over here. We're going to go ahead and take the square root on both sides. So on the left-hand side, my square and my root cancel, remember, but because I have a variable, I am left with the absolute value of 3x minus 11. On the right-hand side, it's just numbers, so my square and my root still basically cancel, but it's just a 15. So remember that squares and roots are inverses, but we're only getting that absolute value when there's a variable, because we don't know what variables are equal to. They could be negative or positive. So now I can write my two solutions, or my two, equations. We'll get two solutions in a minute. So either 3x minus 11 is equal to 15, or 3x minus 11 is equal to negative 15. My first step is to add 11 all the way through. So 3x is equal to 26, or let's see if we can get the second one in here. That zeroes out. 3x is equal to negative 4. Divide by 3. So either x is 26 thirds or x is negative 4 thirds. Barely any space to fit that in there, huh? All right, so main ideas today are just that we have this pattern for perfect squares. So we're going to keep practicing that a lot, where you've got your first term squared, your middle term is the doubled one, the first times the last but doubled, and our last term when we multiply it out is going to be whatever that second part of the binomial was, the last term squared. So we'll work a lot on this pattern. Hopefully this wasn't too confusing. I can see I've got a couple mistakes I need to fix for your notes before I hand them out. And as always, class, if you have questions, please make sure that you ask.